Hello, I'm Carlos Frajuca. First of all, I'd like to thank all the organizers for this wonderful event here that happens every few years. I would like that to be every year, but well, we're here and let's start it. I'm going to tell you about our work we're developing with my student, postgraduate student, André Rogério Prado, in São Paulo Federal Institute, and together with Nadia Simão Magalhães in the São Paulo Federal University, also in Brazil, we are going to present you the challenges of calibrating a laser interferometer gravitational wave detector that, as you know, we have in the recent years the detection of the first detections of gravitational waves. But first, let me explain you a little bit how a laser interferometer gravitational wave detector works. Uh, let's think that a gravitational wave is passing through the detector coming from top to bottom. Here we have interferometer, here we have the laser, here is a beam splitter. The laser is divided in two. It passes through by these two mirrors here, and the laser gets storage between the two mirrors, and it comes back to the beam splitter, come to the photodetector. And we set the experiment, the detector, in a dark fringe detection here in the photodetector. We set that we have no signal in the photodetector. When the gravitational waves pass through, for the equivalent principle, the gravitational wave signals, it also generates an acceleration, and with this acceleration, these masses move, this arm gets shorter, and this one gets longer, and it's going to vibrate. And this change the dark fringe signal here, and as this the length of this arm here it changes as the gravitational wave passes, we have a signal here in the photodetector. Well, but it's good because you have a signal here, but we have a problem here because in the real world these mirrors, they vibrate. They have seismical noise, they have thermal noise, and this um, it not only changes the signal here, but it gets the lock of the detector lost, because as it moves, we don't have the dark fringe in the photodetector more. Not because of the signal, but because of the vibrations here. We have lost the lock of the detector, then the detector doesn't work anymore. That's a problem. It's also a problem for the calibration, because what happens? What's the normal way to calibrate a detector? We inject a known signal in the detector, and this known signal, it also changes the positions of the arms and changes the signal on the photodetector. To avoid that, we as I'm going to show, we add some devices in the mirrors that keep the mirror stable and you don't lose the lock. But to don't lose the lock, you need to mirrors to move less than 1 billionth of the normal seismic noise in the ground. And when you injected the signal, uh, this system, these actuators, they don't know what's the signal or gravitational wave or a vibration is. They direct to the calibration signal, and we can't calibrate the signal in a common way. That's I already told you some information in the abstract. I'm going to show you the outline. I already explained about the laser interferometer gravitation wave detectors. I'm going to RIGWD. I told you something about the locking of the system, why it is needed. I already told you that. I'm going to show you now how these locking active systems they work in the real detectors. Then I'm going to, it will be more clear in the end why I'm going to tell you about the gravitational detection frequency range, because it will be important for what the method we're going to propose to make the calibration. Then to make a comparison with the LIGWD. Well, this is the super attenuator of advanced Virgo. I'm going to hide myself a bit here. This is the super attenuator. The payload here is the mirror. And as you can see, there's a lot of sensor, coils, piezoelectrics in the system, 21 motors. Many of them are used to make the suspension, but as I'm going to show you here, in the very bottom of the suspension, you have this marionette that it actuates to keep the detector locked in the interferometer in the dark fringe configuration. When the system detects that it is losing the locking, it actuates to keep the lock. This is the same. This is how it looks like in the real world. And this is a sketch on actual like the interferometer. It's about the same. We have 20 watts here coming to the interferometer arms. The arms are 4 kilometers long, and you have storage here 100 kilowatts. And in all these mirrors, we have this suspension here. You have some pieces, metal masses connected with steel wires. But the steel wires, they have a creep noise. To avoid that, we have this fused mass here, another fused mass here, where the mirror is. And connecting the two are fused silica fibers. As the fused silica is an amorphous material, they don't have creep noise. But behind the mirror, we have this, with the same suspension, we have this electrostatic actuator. When it feels that it senses that the detector is losing lock, it actuates here and moves the mirror in the correct position to keep the system locked. But that's the problem. How are we going to calibrate the system if you inject some signal data, you're going to move the mirrors, but the electrostatic actuators, you are going to try to keep these mirrors in position, and it's not easy to calibrate it in a normal way. Then I'm going to propose another way to calibrate it. And I'm going just briefly, I'm going to show you, this is the signal of the first gravitational wave detector. This is the actual signal. That will be the signal from the gravitational waves. When you subtract that from the signal, we get this noise here. But what's important? It's important here. This is the real signal. This is the signal in Hanford. This is the signal in Livingston. And what you can see here, the frequency is 128 Hertz. It's around 100 Hertz. So in here and in here. And I'm going to show you the other events already detected in the catalog. You can find that in the LIGO webpage. And here you see the signals. And you can see the maximum amplitude is 128 Hertz in all these events, including this one that is the binary neutron star event with an electromagnetic counterpart that was detected. That's the important part. It was detected with these events, and it happens all in that frequencies below 500 Hertz, because We had in the 90s another kind of gravitational wave detectors. It was the resonant mass gravitational wave detectors. And how it works. It's a mass that when the gravitational wave passes through, it is resonant with the frequency of the gravitational waves and make the mass vibrates in a resonant way. In this way you can detect the signal. This is a bar, it is an electro detector in the United States. It was in the United States. It is a 3 meters long bar. In the end, you have a transducer. But this detector is easily calibrated. Why? Because in the other end of the bar, we have a device that kicks the bar with a no signal. And within this signal here, you can check what's this. We match the energy that the signal that we are kicking with the energy that we have in the transducer. Then you can easily calibrate the signal. This was the detector in the United States. It was cooled to 4 Kelvin, using liquid nitrogen. And we have not only this one, but we had there was a network of detectors. The Lego in the United States, two in Italy, Nautilus and Riga, one in Switzerland, Explorer, and one in Australia, Niobe. But we have this working for almost 2 decades. And why you don't have any signals? Because they worked for historical reasons. Weber first proposed a bar detector, and used these detectors with a reasonable size. We got signals of around 1 kilohertz, and all the signals that the interferometer detector detect was below that, very below that. Then what we're going to propose? We're going to propose make a resonant mass detector, but that works around 128 hertz. It will be very easy to calibrate. We don't need to check all the signal, but you need only to have a signal in that region when you have the biggest amplitude of the signal, and you can use that to calibrate the gravitational, the interferometric detector. And to get this range of frequency, we're going to propose a new kind of transducer, not a bar one, if you need a frequency of 100 hertz, instead of to have a 3 meters bar, you're going to have a 30 meters bar. And this one is like a tuning fork. They have another way to change the frequency. We can change the frequency of this arm here that works as a spring, and we can change the mass of these masses here. Then it's much easier to calibrate that. This one was designed to work at 152 hertz, but we can easily change that by increasing these masses, only increasing the diameter of the detector until I'm going to show you then how it vibrates. It's a very nice vibration because have these two masses vibrating in a parallel way. We're going to have another modes here because it's vibrating at a very small amplitude. To increase this amplitude, we are going to connect in this mass here a second and a third mode with smaller masses that also vibrate. They are resonant, but they have a mechanical amplification. You have a better signal. This is how it is going to work, these modes. This is a second resonant mode. This is the third one. I'm going to call the Sapphire transducer. I'm going to inject here microwaves. that as it changes its size, it changes the resonance, the microwave vibrations inside the sapphire transducer, and this creates sidebands. These sidebands come to the system, and we analyze here, and the amplitude of the sidebands are proportional to the gravitational wave that pass through the masses. Using these parameters, 10 metric tons for the mass is 10 kilos, the last resonant mass 10 grams. For the tuning fork, it was made of niobium. It's a mechanical core 250 million. For the other modes, it's 500 million. A sapphire, it can easily be reached. There are many mechanical factors much bigger than that. Electrical factor for the sapphire is electrical quality factor for sapphire is also very easy to reach. The temperature is not very easy to reach. We make a simulation of 10 millikelvin. We believe you can reach that. The temperature of the amplifier is 4 Kelvin. This is at the FDX, the sensitivity in frequency as the sapphire transducer changes is 3 to 10 to the 14 hertz over meter. This is the noise, the phase noise of the microwave. This is the amplitude noise of the microwave at 100 hertz. Make that we can have these amplitudes here. We have here the strain noise density to reach 10 to the minus 23. The strain intensity we get in overall the frequency is 1.31 times 10 to the minus 21. The strain quantum limit is 1.29 10 to minus 21. Then in this limit we have only one phonon working in the detector. The noise temperature is 6 10 to the minus 9 Kelvin. This is the LIGO sensitivity curve. This is the future. The O3 observation run is that region here. And putting our detector here, we can reach this project. We don't need to reach the curved LIGO because we are interested in the biggest amplitude. And then we can, as a signal path here, we can measure it here and use this signal to calibrate the LIGO detector. That's our idea. The main limitation is the 10 millikelvin. It will be necessary later refrigerator to reach this temperature, but we use that in the chamber, the Brazilian gravitational wave detector chamber, and we make some calculations that using this kind of suspension connecting the dilution refrigerator to the masses, giving enough space, we can get any attenuation that we need to reach these sensitivities that you are interested. Well, that's our idea for how to make one detector to calibrate another detector. And we are very confident that we can reach that because this is the curves of the chamber detector that were made. And this is a 4 Kelvin, and this is at 50 millikelvin, and we increase the sensitivity without losing any sensitivity. Without losing sensitivity because of the vibration. These other curves here are electronic noise. It's not important. This is the Brownian noise and the vibration noise. Okay. Thank you for your attention.